could be high surface area, high accessible absorption site, fine-tuning the compound for pollutant, and ease of reuse. This is a very important feature. Additional things, for example, could be, gold, titanium dioxide for pollutant degradation, photocatalysis, and chemical reduction. And we can see, for example, on the right side, we can see the titanium dioxide. Addition, we can add, for example, silver, carbon nanotubes for removal of contaminants from water. It could be used also for disinfection so the carbon nanotubes and the silver could be used for damaging membrane cell and production of reactive oxygen species. Now, if we look at the trends, where are the trends in nano-enabled membranes? We have the short-term trends, which is what's happening now. We have the medium-term trends, is what is being done in research laboratories. It's not applied yet, but it's being studied in labs. And then we have the long-term, which are the next generation membranes, which have a long path to reach something that can definitely be commercialized. Okay, so these are the different trends. Now, the short-term trends refer to passive surface properties, which are antimicrobial, wetting control, and antifouling. So I'll discuss a little bit about all these features. Then we have the medium-term trend, which looks at active properties. So for example, switchable surfaces, catalytic surfaces, and stimuli responsive. Then we have the long-term, which refers to next generations, nanoporous, and atomic layer. So let's go over the different features. So the passive surface properties by nano, this is what is being done today, okay? And what are the requirements? Well, minor modification to the fabrication process. So these, this type of interface with nanotechnology has minor modifications on the fabrication processes. They could be additive to the polymer fabrication or post-synthesis modification. Okay, so two ways, either being added to the polymer during fabrication or post-synthesis modifications. And they are operational with the current reactors, with the current treatment technologies. So therefore, the interface is very easy. However, they're passive. What does it mean passive? I'll soon explain to you. When we look at passive properties by nano, we look at both antimicrobial and controlled wettability. Both of these are passive technologies. So it's just the inclusion of silver, copper, metal oxides, carbon nanomaterials, and controlled delivery capsules, or controlled wettability. And we want to control here the hydrophilicity, hydrophobicity, or amphiphobic conditions. So antimicrobial membranes, we already discussed this. It refers to nanostructures on polymeric membranes. For example, here, this is a membrane bound with copper nanoparticles after sonication. So we can see here that already this is actually, when we look at the different features, this is post-synthesis modification. So it's just addition of copper nanoparticles onto the RO membrane. And for example, we can see here less flux decline with GOAG, so graphitic oxide with silver. We can see here that, for example, we have less reduction in water flux due to control of biofouling. And here we see also less biocide effect over time. So one of the disadvantages of this type of these type of membranes is we can see that the biocide loses its effectivity over time. We also discussed that before, that we need to really test operational features over time, over a long period of time, to really understand how the membranes operate. So the inclusion of biocides, one of the downsides of it is the biocide can actually reduce its concentration. So we can see a reduction in concentration of silver ion over time. And the time is actually days. Here, for example, we can see the inclusion of geosilver. It actually would preserve the water flux, which is of course is a very good feature. However, this is addition onto already established membranes. Another important feature of passive membranes is the controlled wettability of the membranes. So there's hydrophilic versus hydrophobic membranes, and this for example, if we have 20 degrees, it means that the surface is a super hydrophilic. If we have a larger degree, it means that it's hydrophobic, and above 150 degrees, it's super hydrophobic. When do we need super hydrophilic characteristics versus super hydrophobic characteristics? So for example, with reverse osmosis membranes, we want high hydrophilicity in order to allow the water to pass through the membrane and avoid the fouling. So with RO, we want to have super hydrophilicity, okay? With membrane distillation, on the other side, we want to have very high hydrophobicity, okay, to avoid membrane pore wetting. So therefore, the wettability of the membranes can actually be controlled by either hydrophilic or hydrophobic characteristics. And this can be done by multivalent re-entering of structures. For example, grafting of silica nanoparticles on the nanofibers. So here we have the nanofibers. The silica nanoparticles are grafted on these nanofibers, and they're being used in order to control the hydrophilicity or the hydrophobicity of the membranes. An omniphobic membrane, which repels both water and oil, is, for example, essential for membrane distillation, okay? And also, we can also design a biomimetic inspiration super hydrophobic surfaces. Biomimetic is actually the study, the formation, and the structure or function of biologically produced substances or materials. So, for example, the lotus leaf is a great example of having super hydrophobic natural surfaces, as it provides self-cleaning capacity. Using this as an inspiration for designing of membranes by actually observing the different structures on these leaves and to mimic these structures onto membranes. This could also be done with shark skin. And the idea here is to have like super hydrophobic surfaces. So if we look at biomimetic inspiration, we can design super hydrophobic anti-fouling membranes. And this is, for example, we can see here the extensive fouling on this membrane, but we can also design slippery liquid infused porous surfaces to design a super hydrophobic surface. And this is done by using the surface and nanostructuring, chemical functionalization, lubricant infiltration, and then removal of the excessive unattached lubricant, which will allow the surface to be slippery and super hydrophobic. Okay, so we discussed so far about the short-term development, which are the passive surface properties: antimicrobial, wetting control, and anti-fouling. So all these are passive. Let's now talk a little bit about the medium term, which are the active properties, which refer to switchable surface, catalytic surface, and stimuli responsive. So we discussed a lot about the catalytic properties of membranes by inclusion, for example, of titanium dioxide particles. Photothermal by inclusion of carbon black or gold. and stimuli responsive, which have switchable properties. This requires major modifications to the fabrication process, require fundamentally new model design. So compared to the passive membrane modifications, the active one actually require major modifications to the membrane. So we cannot just take like a purchased membrane and modify it. We actually need to, with active properties of now, we need to design new membranes. So for example, with catalytic titanium dioxide particles, we consider, so we discussed this already numerous times, the nano catalysts are activated by exposure to UV light to generate the reactive oxygen species that can in turn inactivate the microorganisms or break down the micropollutants. And really interesting feature, I think, is the photothermal carbon black. Carbon black nanoparticles are activated by light, and they convert photon energy into thermal energy. And the idea here is actually to enhance water evaporation. The photothermal design is done through management of the heat and the hierarchy of the smooth water flow channels that are evolved in parallel. So this is a conventional MD membrane, and we can see the PVDF membrane, and we have here the evaporation of water, condensation, and the purified water, and this is saline water. With addition of carbon black, we can actually have enhanced evaporation of the water because the carbon black can actually convert solar radiation. It can convert solar radiation into thermal energy, which will increase the evaporation of the water, okay? Increase the rate of evaporation of the water. And therefore, this will actually improve the membrane properties. I think this is a very interesting feature. And here we can see also when we apply, for example, here. So when we apply a high potential and alternating current, so we consider that we're applying an alternating current to a carbon nanotube polymeric composite film. This alternating current actually provides a self-heating membrane, okay? So this provides a self-heating membrane, and this can actually enhance desalination performance of high salinity brines by membrane distillation. So here we are applying a high potential alternating current to the carbon nanotube polymeric composite. It's really interesting. Here we have the titanium electrodes, and this actually enhances desalination. So this is also an active property. Why is it active? Because upon we are imposing a change, and we are getting some type of reaction. So for example, we can, in the previous example, the solar radiation the solar radiation was absorbed by the carbon nanotubes and enhanced evaporation. In this case, we are applying a high potential current to enhance the desalination of membranes. So these are active surfaces. They're active because we are imposing something external onto the membrane, and then the membrane changes its properties or changes its functionalities. So this is very interesting, the study of active membranes. Another type of active membrane is the stimuli responsive switchable properties. And in this case, we have, there is controlled addition of hydrogen peroxide to the membrane. And we can see here, for example, with catalytic ultrafiltration membrane. So here we have the hydrogen peroxide dosing with a high water flux. And then we have, without the hydrogen peroxide dosing, we have a reduced flux, and we have organic pollutant degradation through photocatalysis, through catalytic ultrafiltration, sorry, not photo, only catalytic. So by kind of changing the feed of the hydrogen peroxide to the membrane, we can actually form different responses, okay? We can see here that the water flux is pretty stable. And this actually looks at the hydrogen dosing point. So here we have a high dosing point, and here we have a low dosing point, and we can see how we can switch the properties of the membrane by feeding hydrogen peroxide to the water. So this is actually the active properties, which could be the switchable surfaces, the catalytic surfaces, and the stimuli responsive surfaces. Now, the long-term development of membranes can relate to next generation membranes. So the next generation membranes are nanoporous materials, such as carbon nanotubes, zeolites, and atomic level membranes. These require new fabrication techniques, and none of them are operational yet. So the next membrane generation membranes refer to aquaporins. Natural and artificial water channels, which are shown schematically here, are aquaporins. Aquaporins is a membrane protein. Carbon nanotubes, self-assembled microcycle-based nanotubes, and single molecular channels. To make a selective layer, the channels are assembled within an amphiphilic polymeric matrix. So this is one type of next generation membrane. And another type is using nanoporous graphene and aligned nanotube membranes. So with this, I would like to kind of move to a different topic that I thought is very interesting with the use of nanotechnology. And this is related to antibiotic nanomaterials. So I think this topic is very interesting. And this is just to show a publication on this topic. So antibiotic resistant bacterial infections, or ARBs, ARB is antibiotic resistant bacteria. ARB infections arise from the acquired resistance or through biofilm formation, and necessitates the development of innovative outside of the box therapeutics. Nanomaterial-based therapeutics are promising tools as they can combat bacterial infections, which are really difficult to treat, featuring the capacity to invade existing mechanisms associated with acquired drug resistance. In addition, the unique size and physical properties of the nanomaterials give them the capability to target biofilms, overcoming recalcitrant infections. So the base mode of action is either bactericidal to kill the bacterial cells, or bacteriostatic to stop bacterial division. And the base of the spectrum of the action could be broad spectrum, like if we look at antibiotics, for example, tetracycline, or narrow spectrum, which is penicillin. Now, the general concept of antibiotic resistant, for example, we can see in this figure a bunch of bacteria, including only one resistant variety. Upon exposure to antibiotics, all the bacteria are dead, And there's one resistant one that is actually surviving, and another normal bacteria that survived. Now, the resistant bacteria multiply and become more common. Eventually, the entire infection evolves into a resistant strain, okay? So, for example, vancomycin strongly inhibits gram-positive bacteria. However, vancomycin also has a strong ear and kidney toxicity. One way to improve treatment is to increase drug delivery to the desired location, thus limiting the amount of drug reaching our organs where it's not necessary, okay? Therefore, with the help of nanoparticle carriers, we can actually design vancomycin modified mesoporous silica nanoparticles. And once we design, they're made to detect and kill only the pathogenic gram-positive bacteria selectively over other cells that we don't want to kill. So how is this related to water? Well, what we can see here is that specifically designed antibiotic and nanoparticles were carriers for vancomycin modified mesoporous silica nanoparticles, and actually this design allowed target medicine. Now, this concept could also be used with applying in water. So nanomaterials have a broad spectrum action. Antimicrobial nanomaterials induce cell inactivation by multiple mechanisms. So can we design antimicrobial nanomaterials to actually disinfect in water what we want to disinfect and actually not disinfect bacteria that are harmless? In addition to that, something to consider is that metal ions also induce toxicity by multiple mechanisms. So the idea, can we develop targeted antimicrobial activity in water using antibiotic nanomaterials? And now antibiotic nanomaterials, they can have multiple mechanisms on cell membrane damage. So for example, it could be chemical interactions, which relate to oxidation and degradation. Electronic, which is surface interaction, and physical, which is mechanical interactions. And this relates to all the biological molecules and cellular structures. And this is the bacteria. This is the nanomaterial, and this is lipid vesicles. And actually, these lipid vesicles that are actually inserted into the nanomaterial can result in inactivation even of human coronavirus, for example. So what is the biofouling problem? I think we discussed the biofouling problem in numerous times. So actually, just to recap, nanoparticles can not only can they combat bacterial and microbial resistance themselves that I mentioned earlier, but they can actually serve as a medium and carrier for antibiotics. Now, this is a very important feature. As a carrier, so if nanoparticles are a carrier for delivery of antibiotics, the main advantages of nanoparticles compared to conventional delivery systems are as follows. They have a very ultra small size. We can control the size of the nanoparticles, as we know, and it's suitable for conducting antimicrobial operations. So it's like really, really specific operation and combating intracellular bacteria and even increasing the specificity, being specific on what we want to, on the mechanisms that we want to target. So antibiotic nanomaterials with controlled delivery of biocide. This is a very important feature. For example, it was found here in the study that silver makes antibiotics thousands of times more effective. So by inclusion of nanomaterials into the antibiotics, it actually specifically disrupted the membrane, and And resistant to antibiotics and to nanomaterials may evolve over time. We don't know this yet. So antibiotic nanomaterials versus free biocides, there are advantages and disadvantages. I'll just not go over all this, but just to make it sure, the advantages are targeted drug delivery. A disadvantage is accumulation of intravenously injected nanomaterials in tissues and organs, okay? It can result in nanotoxicity. So these could be advantages and disadvantages. And how can we take this nano antibiotics into the water? I'm not sure, but I think this could be an interesting feature if we can actually apply nanoparticles as a carriers for specifically targeting specific bacterial contamination in water. Possibly it could be something that has interesting, as already the medical research scientists are already researching this on humans. But currently, silver nanoparticles, for example, could be used for antimicrobial surfaces. So it's not really targeting different microorganisms free swimming in the water, but it's actually including the silver nanoparticles onto surfaces. And this is something that already is known, that we can design anti-fouling surfaces that prevent bacterial adhesion. Okay. So we also can design surfaces in water. So for example, piping systems. So we know that we have biofilm formation on piping systems. We have biofilm formation on membranes. So maybe we can design antimicrobial surfaces to prevent bacterial adhesion. Okay. Actually, antimicrobial surfaces are one of the most promising innovations to prevent bacterial adhesion and transmission in hospital environments. Various heavy metal compounds, including titanium dioxide, copper oxide, zinc oxide, and silver are known to have these properties. By the way, silver vessels is something that was known like 1000 BC, so it's not new, but the idea is to take the silver nanoparticles to damage the DNA or RNA or inactivate the enzymes. This is something that that was recently studied. These nanoparticles, as we already discussed when we discussed toxicity, they can increase the membrane permeability and change the structure of the membrane due to the inclusion of silver nanoparticles, and can be an alternative antimicrobial treatment. Okay, so how can we take this to the next step? So as I see it, the next step, like has like really interesting features. I think that in order to make things practical and to make, for example, to design the new generation of membranes, for example, the biomimetic membranes, and also to design the active membranes and all these things, to design antibiotic nanoparticles, to target disinfect different viruses in water, for example. So today, for example, the disinfectants in water are broad range. We insert into the water chlorine, expose it to UV, ozone, whatever, and it will kill all the microorganisms. Maybe that's not required. Maybe we can only disinfect targeted microorganisms. Maybe we can design membranes that would be active, that when we impose a stimuli on the membrane, that membrane will result in either a thermal change, electric change, chemical change. So we can actually tune when we want to do everything. Maybe when we clean the membrane, so we didn't discuss this a lot, but when we clean the membranes following operation, so when we do the backwash, we don't need to impose that stimuli, and we will oppose only the stimuli upon specific conditions. So the stimuli could be chemical, it could be by electrical charge, it could be by solar radiation. And we can that way stimulate the membrane for different reactions. So the membrane is active. We activate the membrane and the possible inventions are endless. So in addition to that, in water treatment systems, and we can incorporate antimicrobial surfaces. We have now a project with Northwestern University in the US. We're working on antimicrobial surfaces in order to avoid and disinfect, in order to avoid attachment of microorganisms. And also we're working on surfaces that even if they have attachment of viruses, for example, upon exposure to light, these surfaces will activate free radicals, which will kill those viruses. So this is kind of an active process because we're imposing something to the membrane or to the surface in order to activate these things. The surfaces that we're using are considered transparent surfaces because these surfaces, for example, if are successful, could be, for example, on our cellular phone. So sometimes we need high throughput surfaces, which allow also to be tuned upon exposure. And in addition to that, would actually be transparent. So just remember with our cellular phone, if once we have the cover on our phone, we want it to be transparent because we want to see what's happening. Similarly, with water treatment processes, so sometimes we don't want to have coatings that are not transparent. We need sometimes transparency. So designing high throughput transparent coatings that will allow also to be, antimicrobial upon exposure of light is very important. Now, again, light is a huge thing. I told you my expertise is light. It's very important to understand what are the wavelengths, what are the intensity. There are different mechanisms that we can impose on microorganisms with different intensities or combinations of them. And I believe that light emitting diodes is the next thing. And similarly, like LEDs is the thing in visible light. It will be also the thing in UVB-based light. Because they're small, we can target them. We can also, I had like a thought that we can also include the LEDs inside the membranes to produce light guides, for example. And this light will actually shine inside the membrane and activate the responses that we want, and we can control it with a controller. So there are many options how to design new things, yeah, could be interesting. So why antimicrobial nano is better than in biomedical settings? It's smaller quantities, shorter time frame, limited environmental release. Okay, let's move on. Yeah, let's move on. Okay. So during this course, we went through a path and we started with different things. So for example, we discussed a little bit about the introduction. So we discussed a little bit about many things. So the introduction to water, the need for water treatment, the conventional water treatment methods and its drawbacks, the drawbacks of the conventional water treatment methods, importance of nanotechnology. Okay, then we discussed why nanotechnology or nanomaterials. We discussed a little bit about synthesis because the course goal was not to discuss about synthesis, it's to discuss the interaction between nanotechnology and water in the aquatic environment. I would say we didn't discuss so much about the history, discuss a little bit about the classification of nanomaterials, the general application of nanomaterials, the application of nanomaterials in water treatment. Now, generally speaking, material engineers, material chemists, whatever, they know how to synthesize materials, everything perfect. Water engineers, environmental engineers, they know how to look at the big picture. Okay, we look at the big picture of where the water flows, where it goes, looking at the recycling issues, looking at the sludge generated, thinking how to improve the treatment, how to use, as environmental engineers, we actually use different disciplines and incorporate them to make a better technology to serve society. Our goal is actually to serve society. So therefore, nanomaterials can be used to serve society. They can be used to make better water. They can be used to target the sustainable development goals. However, it must be done safely. It's not that we can do whatever we want and release these particles to the aquatic environment without any consequences. So therefore, it's really important to work together from different disciplines, because I'm not an expert in synthesis of nanoparticles. I don't need to be an expert. If I want expertise, I cooperate with people that are experts. I come with my expertise, looking at the big picture, looking at the water treatment, recycling, thinking which considerations we need to take when we design systems and stuff like that. So the application of nanomaterials in water treatment necessitates different types of expertise. Also people that are expert in energy. Also people, if we look at switchable, tunable membranes, we need people expert in sensors. So we need to develop teams to solve the huge water issues. Then we discussed the importance of nanomaterials in water treatment, the current water treatment applications of nanomaterials, the mechanisms for pollutant removal, nanomaterial toxicity, and conclusion. So kind of like the path of this course went like this path, okay, until we reach this point today. And I'll just continue to talk about a few features that I thought they were interesting. Okay, so when we, okay, one of the challenges for nanomaterials before entering the aquatic environment, we need to develop non-toxic stable nanomaterials. We need to have effective recovery, regeneration, and reuse of nanomaterials. So this third line is really important. Is it done in the scientific literature? No. So the idea is that the development of nanotechnologies and nanomaterials is not done concurrently with the environmental consequences. This is how we are, and this is how we kind of I would just say, ruin our planet. We design things, we make things, and then we think, okay, we ruined our planet. What the hell? Now what we're doing? How are we going to now reverse back and fix everything that we've done? We know that the tipping point, we have maybe a 7-8 tipping point for climate change until we reach the 1.5 degrees Celsius. For example, in my university, we made a new course on climate change. Each lecture was a scientist from different disciplines. So I mostly spoke about technologies and how we can design technologies to compact the climate change changes as mitigation and treatment. But what we do as humans, we make problems and then we think how to solve them. But we need to think while we're synthesizing, while we're designing new things, we need to work together with people that are expert in understanding the toxicity, people that are expert in understanding leaching to water, people that are expert in water quality analysis to understand, and people that are expert in biofilms to understand, are these biocides so for example, today we can publish papers on designing inclusion of a biocide into a membrane. But did you test it for a long time? Do you know what happens next week even? So we really need to be socially responsive to the science that we're doing. And the problem is that the grants do not support this type of research. What do the grants support? The grants support research on making new things, designing new materials, designing new membranes, designing new treatment solutions, blah, blah, blah. If you want to, for example, submit a research grant on I want to see what's happening with this membrane for months. Please give me money to research that. I want to understand if there's leaching of nanoparticles to the water. Please support me on doing this because I want to learn about the environmental consequences of new technology being designed. Still not get the funding. So the problem is the system. I know like other scientists minded like me that are really interested in understanding consequences of treatment technologies. However, unfortunately, these are issues that also our granting system must actually think in. And that's why I was like happy about this course because we didn't talk about synthesis of nanoparticles. We talked about the interaction between nanoparticles and water and wastewater. But we must look at recovery. We must look at regeneration. We must look at cleaning of membranes over time. We must look at the reuse of nanomaterials. We must develop processes to reduce the nanotoxicity. So the R's of sustainability are refuse, reduce, reuse, recycle, and recover. This is sustainability. Before the break, I just want to talk about a little bit about challenges and remedies. Research into products and new applications of nanomaterials in our daily life continues to increase in number and variety. To protect the environment and the living organisms, it is necessary to know the toxic doses of the nanoparticles and the mechanisms of their toxicity. With newer nanomaterials, and this is an important point, based products being introduced into the market on a daily basis, there is an urgent need to reduce the knowledge gap between the physical chemical properties in the aquatic environment and their influence on the manifestation of toxicity issues. I can tell you that I submitted numerous grants on the impact of what, so we have in our university a nano center, and they design and synthesize and they get cheers. Okay. I tried to many times submit grants, and not only in the, like also elsewhere, international stuff like that, trying to, not only me, also with my colleagues, trying to understand not necessarily the toxicity, but tracking different treatment steps and trying to see what happens to these particles, either if they're natural or engineered or doesn't matter. Trying to follow the track, trying to track what's happening over different processes. Can we modify, for example, the treatment processes in wastewater and sewage to reduce the exposure to these particles? Maybe these particles are not an issue because maybe they aggregate and they don't impose an issue. But I still believe that if we use, for example, membranes with biocides, we really need to understand what's happening to the environment in that case. But on the other hand, we have so many environmental challenges, then how can we target which challenge should we concentrate on? And these are like big questions and big issues. Research into new analytical methods is also required to address special properties of nanomaterials. And also, this is kind of the key point before we go to the break. A multidisciplinary team effort from material scientists, molecular biologists, toxicologists, physicists, environmental engineers, really need to kind of like work together to facilitate the interlinking of different facets of nanotechnology and to understand the exposure and mechanisms involved, both on the cellular level and the engineering level. So we kind of need to move between dimensions. We need to understand that the nanotechnology is the nano dimension, but it has an impact on the big dimension, and kind of like we need to find a way to understand how this technology, which new materials are being synthesized every day. I would say that that this is a huge market. As you saw when we discussed the market for nanomaterials, the market is only growing and growing and growing and growing. So we will be exposed more and more and more to nano-based materials everywhere. And how are we addressing pollution? So this is an important point. I would say also that just even looking at how do we address the face mask with the corona crisis and all the medical waste, all the syringes, needles, face masks, even when we need to do the antigen testing, we have tons of waste generated. And like with everything that we're doing, we are generating waste. We're not taking consequences of what we're doing. And and this is really a challenge. Like, when do we take care of the environment? At what point do we think about the water, how it's getting contaminated and stuff like that? So I think we will take a break. Is 10 minutes okay? Let's take like a 10-minute break, okay? So can we, what is now the local time?
It's 3:25.
3:25? Oh, with mine it's 3:20. Are you
Yeah,
sure?
what? It's 3:25. It's 3:25 here.
Really?
Yeah.
Okay, so let's take a break to 3:35. Is that okay?
Yeah, perfect. No issues.
Okay, thanks. I'm asking because I have to make like conversion while I'm talking. So although I'm multidisciplined still.
Okay. Okay.
So 10 minutes break and we'll return back. Thank you.
Okay. Fine.
Hi, hello, everyone.
Yeah, hi, madam.
Okay, good. So let's return back. So we discussed a little bit about the challenges and the remedies. And let's discuss about a few more issues. Okay, okay, good. So we will discuss just a little bit more, a few points, and then me and Dr. Birani, he will also summarize the course, and then we will kind of have like discussions on where to next. Between all of us, what is the next step? So I really I don't want to go over all these slides. I think I prefer to have for us a little bit time for discussion. Open discussion. I would like to just a little bit show about this scheme, which actually illustrates the translation of materials from lab scale to the market. Okay, so this is something that I think is very important. How we translate from the lab to the market, okay? So it's very difficult to see what's happening in the scheme. But we have here, for example, metal oxide-based nanomaterials, carbon materials and their composites, nanopolymers and their derivatives. So this is this small circle, okay? Then we have the larger circle. So this circle is the circle of material synthesis. Then we have the larger circle of incorporating these materials into systems, into reactors, in order to have something happening actually. So, for example, this is inclusion of nanomaterials or nanoparticles for catalysis or photocatalysis, for purification, for disinfection, atmospheric water harvesting. So this is still in the lab phase. Then we need to go to the community scale. The community scale is community scale desalination. So for example, community scale drinking water CDI machine for rural areas. Community scale contaminant removal. So for example, nanoparticle-based arsenic filtration pump used by school children in West Bengal. And for example, an atmospheric water generation with a capacity of 400 liters per day. So it's going from the design and the synthesis to the technologies to the wide scale implementation, okay, which is the third circle, okay. A few new important features, for example, is use of nanomaterials for sensing and monitoring of water quality parameters. So for example, nanomaterials are known, and we already discussed this, to have excellent electrical, optical, thermal, and catalytic properties and strong mechanical strength, and they give us wide opportunities to construct nanomaterials-based sensors or devices that can actually be used for monitoring environmental contamination in air, water, and soil. So various nanomaterials, such as carbon nanotubes, gold nanoparticles, silicon nanowires, and quantum dots, have been extensively explored for detection and measuring, for example, toxic metal ions, pesticides, and hazardous industrial-based chemicals. So for example, if we look at this thing, we see here a DNA microarray that captures the DNA specific for each target. This was assembled on a surface. So this is the bacterial cells. The RNA was extracted from the cells. It was fragmented, and after that, it was assembled on a surface for resonance imaging. And the surface had gold coated nanoprisms. Upon hybridization of the DNA with isolated 16 rRNA there was a change in the reflectivity of the gold-coated nanoprisms, which allowed detection and enhanced sensitivity. So the gold nanoparticles were functionalized with a detection probe that can introduce a simple way to analyze RNA concentration as low as 10 picograms per milliliter. So this is how nanomaterials can be used in sensing. Let's move on. Nanomaterials and micromotors have been considered to convert energy from several resources into machine driving forces, okay? Empowering them to achieve specific goals through various mechanisms. These innovative motors are motorized in the cases of using fuel or without fuel sources. So it could be acoustic, magnetic field, electrical field. And they have several exciting applications. So different mechanisms employed by nanomicromotors for treatment of water pollutant are graphically shown in this figure, okay? So here we have the removal mechanisms, adsorption of organic pollutants, toxic metal and oil pollutants, and the removal of them using nano and micromotors. Another interesting feature, I will not talk about this. Okay, just a little bit about this. No, let's move on. Okay, okay, so this is actually an important feature that I think we also must consider in reactor design. So based on the highly efficient absorption and desorption properties and condensation of organic wastewater could be realized, and how could that be done? So after comprehensive evaluation of carbon nanomaterials-based absorbents, the concentration factor could be 10 to 20 times after one stage absorption-desorption process, which means that here we have 100% organic wastewater, and here we have the different materials, we can meet the standard after adsorption. Now, afterwards, we need to recycle the adsorbed material, and we need to recycle it and then separate it from the stream and treat it in order to have the process more sustainable. So this is like also an important feature. Another interesting feature is application of 3D printed macrostructures containing titanium dioxide nanoparticles. And this is for direct absorption removal of arsenic in water. As you can see in the figure. So different titanium dioxide nanoparticles were used as absorbents, and they were initially doped into the resin. Okay, so titanium nanoparticles were absorbed into the resin, and they were used extruded through 3D printing machines to 3D print different macrostructures that has the resin. So the resin could be, for example, PLA, polylactic acid, or something like that, with inclusion of nanoparticles into it, and then 3D printing different structures. And the structure itself could be like, for example, like a structure of a filter, and then the water, and that could be used actually to absorb arsenic from groundwater. So it's kind of like it's kind of like an easy way. Still, 3D printing is expensive, but there will be a day that it will not be expensive. Our findings show that 3D printing provides a promising route for design and fabrication of customized macro surfaces. And this is also an interesting feature. Now let's go on. No, let's move on. Okay, so okay, so as we discussed, nanotechnology is a highly interdisciplinary study. It embraces concepts from various fields. It's a beautiful concept from chemistry, physics, molecular biology, material science, electrical, mechanical engineering, applied mathematics, and so on, computer science, and so on and so forth. Nanotechnology lies at the intersection of these scientific and engineering disciplines. These materials are confined to the nanoscale range, and they can have novel optical, electrical, computational, mechanical, chemical properties in comparison to the same material at the larger scale. These nanomaterials are expected to deliver products with superior mechanical strength, higher computational speed, and increased efficiency, because we discussed all these things. Nanotechnology is expected to find novel solutions for long-standing real-world problems and to have a large impact on the global economy as being today, but it will even be more increased. The next generation of many consumer products ranging from computer chips to batteries, cosmetics, will use nanotechnology. Such products are related to services, are expected to be at the base of the new global multi-trillion-dollar economy with nanomaterials. Unfortunately, as nanotechnologies and products increase, nanoproducts entering the aquatic ecosystem and other water systems will increase as well, thereby increasing the potential threat to aquatic organisms and to the aquatic environment. And the last slide, before we kind of summarize things, the main sources of nanomaterials that pollute aquatic environment, they derive from the households, from the residential households. Also in materials in textile clothes that we're wearing, cosmetics, food packaging, and medicine. Nanomaterials released from textile will reach sewage systems and eventually wastewater treatment plants if they go to the wastewater treatment plant. A portion of the wastewater is retained in septic tanks, which may pollute also groundwater sources. Other sources of pollution from nanomaterials are releases from industrial waste, from production sites, hospitals, and medical centers and clinics. The sources of nanomaterials released to the terrestrial environment may reach surface or groundwater, include also packaging materials for consumer cosmetics, food, medical waste, pharmaceuticals that also contain nanomaterials. And with that, I would like to give the floor to Dr. Barani and then Dr. Ram, and then we can have some conclusions. Dr. Barani, do you want to conclude? Can anyone hear me or? Okay, yeah, you can hear. Yeah, do you want to conclude? Say your take-home message.
Yeah. So one such thing is that I think first I thought of listening from the audience what they feel. Then I thought of concluding it. So.
Okay.
Hello? Yeah. Am I audible?
Yeah. Can we also see you, Barani? It would be nice if we can.
Yeah.
Thank you.
Yeah. So I think.
Where's your background slide?
Yeah. It got changed because the host got changed and then everything gets changed.
Oh.
Yeah. Every time I need to keep changing because I keep shuffling.
Good. Okay.
So just a minute. Okay. So I just want first the audience to speak out what all the things that they took it from this course rather than we speaking out, because we have been speaking for the past 5 days. And then, so I feel the audience, if they have anything to add upon, then it will be good enough, I feel. Yeah, participants.
Please speak out, or I'm picking someone according to the name. It's your choice.
Okay, I think no one is ready. Everyone is shy, it seems. Yeah, anyone from the participants who can? Yeah, someone is there.
Good evening, sir. Barani sir, good evening.
Yeah. It's Padma.
Yeah, good evening, Hadas. Yeah, the program was like the entire duration of 14th to 18th was very nice, and the program was scheduled in such a way that we have started from the basics of chemistry even, and we have started escalated towards nanotechnology and its advancements. And the last day was like what are all the challenges we will be facing throughout the usage of nanomaterials in different perspectives of water treatment. And one advantageous thing is it's not about only nano photocatalytic processes. The program emphasized more towards membranes also, and the toxicity predictions also. I think it has given a wonderful platform towards the toxicity analysis too. And, that way, it stands. It's wonderful. The duration of 14 to 18, the 5 days of time was much useful for us. Thank you.
Thank you, Padma. Okay, anyone else?
Hello.
Yes.
Yeah. Thank you, sir. So thank you, Hadas ma'am, and thank you, sir, for giving this opportunity. So just one point I wanted to mention that I'm working in the field of microfluidics, so rheology and electrohydrodynamics. So I was planning to work on a microfluidic system to for synthesis of nanoparticles. So this is actually, but this is the first time since like I have attended a course wherein I got to see the like a real applications, developing the applications from lab to pilot scale, and the problems which are faced in that scaling the system. So this is a great opportunity to see the first time like being a researcher, what should be the vision for the research work. So thank you for giving this opportunity. Thank you.
Thank you, Chinta.
Thank you very much. Thank you.
Yeah, any other participants who wanted to have their view upon the course can add upon?
Yes, sir. A very good afternoon to all of you, sir.
Yeah.
Sir, it was really a informative workshop for me as a chemistry student and working on physicochemical characterization and water purification. Really, it will help me a lot. Whatever I got, I will apply this. And overall, it was very good workshop. In future, more such workshops should be organized. Thank you very much.
Thank you, Sunil.
Thank you very much. Thank you.
I think, okay, before anyone joins, then I think I can summarize the whole picture of our workshop. The motive was to not only look with respect to the water, but still the applications or the usage of nanomaterials as such. It can't be confined only to one segment or one domain. So nanoparticles finds its application in water. It finds an application in wastewater treated, especially the industrial wastewater, and then photocatalysis is one such technique where again membranes, usage of membranes for treating water, wastewater. Again, these are the areas which though we had the title of water treatment, but still we could not able to resist speaking about the other areas. So in that way, I think it has opened the gates for other areas as well. And the second point that the nanoparticles challenges, how to detect them in environment, as spoken by Hadas, as it is an interdisciplinary, more people needs to come in order to join hands to take up the work, because it is not one researcher can't be able to complete the whole picture of nanoparticles usage, because it involves different domains or different specialists to know about especially the toxicity to the plants, to the when it comes to food cycle, the risk assessment, and then life cycle assessment. That is also needed on a picture. What is the impact that the nanoparticles or the nanomaterial has over to the system as well as to the whole of the environment. So we had, though we had spoken about the release of nanoparticles into the water, but still the whole picture of these nanomaterials in the product, when it is there as a consumer product, what is the impact that it has onto the environment? How long does it stay? What is the impact? Quantification with respect to environmental impact categories such as global warming potential or eutrophication potential or acidification potential is still one such area where people can really focus upon and then take up a work. Though the applications, as I have highlighted, that the applications of nanomaterial has been in different domains, but still the whole complete life cycle, and still the another challenge is that the usage of nanoparticle in different consumer product itself has not been documented. When you want to take up a life cycle assessment, then again the concentration, the quantity in which it is being used to products, what is their lifetime, how does it get transported, everything needs to be taken into consideration. So this involves a team effort in order to see as a whole. Then only you will be able to sense their presence and then quantify their presence, detect their presence, especially in the environment. Though once whatever we spoke, or the highlight was to use nanomaterials for water treatment, but again in one of the topic that we were discussing, nanoparticles, once it comes into wastewater, how does it behave? What is the toxicity that it has onto the environment is one such thing that still it can be explored. And then the life cycle aspect of these nanoparticles in the environment can be still pitched in by other researchers, and then they can take it forward. So yeah, over to you, Hadas. You have anything to add? Yeah.
I see also that Ram is here.
Yeah, Ram is here. Yeah, Ram is here.
Yeah, I mean, am I audible, Dr. Barney?
Yes, sir.
Yes.
Yeah, you're audible.
Yes, please.
Yeah. Thank you everyone for your participation over here. And Dr. Barney and Dr. Hadas took everything onto the role, and they have structured a Pakka nanomaterial part of it, right? And they have given you a lot of research direction, and the real outcome is like if any one of you take a few points out of here and execute in the field, that would be great. And that when we see that as a possible publication, and if we are able to recognize your name, that gives the real output of this 14 to 18. And as I hope it is Dr. V. Padmanabhan or soon become a Dr. Padmanabhan, whatever may be the case. If that one name got registered, and if I got see the publication in future, it will be greatest happiness from our side. And one thing I just like to highlight over here is like, yes, there is damn sure nanomaterial application, but the cost of doing everything is, the cost associated is a little bit higher for experimental study. So we have a lot of experiments. Now there should be a transformation towards modeling too. That one thing I like to emphasize here, and soon we are planning for modeling aspects, which Dr. Barney will be explaining at the closure of this entire feedback session. Over to you, Dr. Barney.
Thank you, Dr. Ram, for your words. And yes, as spoke by Dr. Ram, we are also planning to have still the behavior, one such behavior in the nanoparticles behavior, and then how to model their concentration in the real-time environment is one such challenging thing. And then we are looking into that aspect as well. Though there are modeling people who are working in modeling with respect to the nanoparticle, but still in order to quantify them or to make get to a massive scale, or otherwise to get the concentration of the nanoparticles in the real-time environment is still one such challenging thing. For that, we need lab scale study as well as mathematical analysis as well. So again, surface, subsurface, again, there are different domains where one can pick up. And then one such area that we are possibly we are looking in future is about how modeling, with the help of modeling, to arrive at the concentration of these nano-sized particles, especially in the subsurface water. So that is where that we are really looking upon. And so that is one such course that we will be also looking forward to float in the coming future.
That's wonderful. Really. Does anyone else want to comment? Add a viewpoint on anything related? Maybe things that you're worried about. How you see if your future is related in some way to nanotechnology, if that's how you see your future. It doesn't have to be about the course. Just wondering like about your background and if you plan to use nanotechnology as part of your what you're doing in your research and stuff like that. Okay, if not, maybe I'll just say something. I have now in my lab two postdocs from India. One actually that one of the postdocs actually she went from India to Japan, and Japan she came to my lab, and another one and two postdocs that recently finished, one after 4 years being in my lab, another one 2 years. And actually all of the postdocs, they have background in chemistry and material science and material engineering. And I think that from these discussions, I kind of took a few key messages. One key message is that I learned to push myself to understand something in a field that I was never educated at. Okay, so I'm not a material engineer. I'm a chemical engineer, but by the way, chemical engineers are not expert in chemistry, although everyone thinks they are. We're actually more like mechanical engineers, but if mechanical engineers discuss more heat transfer, we talk more about mass transfer. So we take the chemical concept into engineering. We don't dive deep into how to put A plus B to get C. So like dealing with something that is highly material based, highly chemical based is a challenge for me as environmental engineer. But I understand that we must have common ground, right? Like you must learn a little bit more about the environment, sustainability principles. These are methodological things. Also like modeling with respect to sustainability. These are things that are very, and also we need to learn a little bit more to understand about how to synthesize and these things. And it's a challenge, but it's a challenge that we kind of must work together. And so when one of my postdocs that he was working on arsenic removal. I think I told you that before. I asked him, listen, before we start, make a table. Let's see the conditions where arsenic is removed. And I was like puzzled because most of the table, I just kind of like put blank. We cannot have pH 2. We cannot have this temperature. We cannot have these conditions. This was not tested in real. So we kind of tried to scan to see, okay, try to think, if we want to make something environmental, right? If this is our goal and our purpose, then we must put the effort to understand how it will be environmental, even if we pay a little bit with efficiency. So this is kind of something that, I don't know, I think it's very important. Ram, I see that you're smiling, so I know that you want to say something.
Yeah, to respond to Dr. Hadas, two takeaways for the participants over here. One takeaway is like to the people I see, like people are from research scholars are there inside, and those who have completed recently their doctorate, you have an opportunity of going for a postdoc with Dr. Hadas. That's the first takeaway I see clearly from this talk. And I had been associated with Dr. Hadas for the past, say, about 5 years. I think that those who are looking for a postdoc, she'll be a very interesting person because she challenges every new concepts and new thought process. To say a few words, I'm a water resource engineer. I'm a systems person. And right now I'm working, I had my hands into nanotechnology. Maybe the inspiration may be Dr. Hadas when she came to India and when we had a work onto it. So that's the first key point I would like to take to, say or respond to the Dr. Hadas. And I request participants to have a conversation and take it forward if it is useful for you. And the second one to respond, as she said, yes, whatever maybe we are looking forward, we just need to look the entire as a system, right? When I thought as a systems person, when I entered into this field, I felt like everyone is dealing with each and every individual component selectively. But nature works in a systematic arrangement. So that has to be taken into consideration when you are doing your research, or if that can be thought of, and that will be the very good essence of the research. And don't believe like only you can do every concept. So it's always better to collaborate with the people and take it forward. That's what I'd like to expand my thought. And this team, what you see today here, me belong to systems area, and Dr. Hadas into advanced oxidation process, and Dr. Bharani, he's into AOP and he's into LCA. So it's a different combo of people out here. So everything comes out of collaboration. So try to collaborate and take it forward. That's what I want to respond, Dr. Hadas, to you. Over to you, Dr. Hadas.
By the way, so with Ram, okay, so I came to KCT in Coimbatore through my university. There's someone that his name is Gary. It doesn't matter, you'll not understand anyway. So I came to Coimbatore and kind of I got to know their Ram and other people from KCT. Then at some other point, see how things get connected. At some other point, I tried to think, where will I do my sabbatical? So I had like offers in the US and places, and my heart was to do my sabbatical in India. So I contacted a few universities. One of them is in IIT Madras in Chennai, Professor Mohan, which I kind of also got to know him, and then I got to learn, or maybe I knew before, but I forgot that Professor Mohan was your advisor. So that was so that was like how things get interconnected. And then Ram, I think you introduced me to Bharani, right? Like I just I'm not sure how, like with this Corona crisis, like so many things are happening. But yes, so then we also worked together on textile waste, and we published a paper together on textile contamination of textile wastewater from the Silgumai area in Coimbatore. So it was very exciting research, and yeah, I think yeah. So I just thought it was like really interesting how things are interconnected, even between humans, not only with nanoparticles.
Okay. So, okay. Any other participants? Any of your views? You have anything to add upon? You would like to hear from the participant rather than we three speaking.
Yeah, because they're not speaking. speaking. Yeah, but please, if anyone wants to say anything, please There is a question here. Maybe maybe it's okay if we read it because I see it's for everyone. I want to do a PhD abroad, but require good research around it. Is there any advice on how to get internships? Oh, wow. Do you have any advice?
It's all about the visiting card would be just only the research article. So if you can able to get one or two, then you can approach the foreign person whom the area that you are working. You can drop an email. That is how it works. Or otherwise, you can. I think this is how I used to communicate. Professor Hadas, if you have any other, you can add upon.
Yeah. Well. I think that, yeah, first, I think that in the academic life, the competition is very fierce. Also for getting an academic position. It's highly competitive. I think it's becoming more and more competitive since more people are studying and yeah, so it is a challenge, but challenges are something that we only need to overcome. I mean, it's not something that we should be afraid of. So, for example, when I wanted to do my my PhD, my father told me just go to the US, and I said okay. And I kind of contacted researchers. I sent them emails. And one of them was at Duke University dealing with UV, and he replied. Not everyone replied. And that's how kind of the interaction started, which had a huge impact on my entire research career. So I would say try to stand out. Even grades is not the only way to stand out. And unfortunately, it is many times the way that things are being classified, but grades is not the only important thing. I, for example, took a student. It doesn't matter, of course, I'm not saying that had dyslective problems or stuff like that. But some people sometimes are very innovative in their mind, and it's not necessarily translated to grades. So it kind of like. Do your best and don't give up. If this is what you want and this is your dream, follow it and just try to make it happen. Yeah, I would say, but sometimes we have multiple dreams. So sometimes we have multiple dreams in our lives, like in the academic life and what we want to research or in general. And so sometimes if one path does not go, we can go to another path. Then it's also okay. Just think about how the nanoparticles, they have different functionalities. We can go through different paths in life. For me, I knew that I want to be a faculty. Like I knew that. I didn't have any other path in mind. Like for me, that was the only path. But for other people, it's different. So yeah, because that was my only path, I said it's either this or nothing. And that was my approach. But it really depends. If you have multiple things that interest you, then if you get the internship, fine. If not, then do something else. If this is only what you want, really, 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 and you're sure about it, then talk to people, contact people, show that you're special, different, stuff like that. Yeah, don't give up. I don't know. That's what I have to say about it. And yes, I thank you for all the kind messages in the chat. That's really wonderful and heartwarming. Yeah. Anything else? Barani, Ram, students?
Okay.
But I think that.
Okay, ma'am, thanks a lot. Okay.
First, I must say that I was also challenged by this course, and I'm sure Barani was, and Ram. It's also for us a challenge, by the way, to teach. It's not only for students to learn, it's for the teachers to teach, also a challenge.
Sure.
And it's a dual street challenge for us to teach and for you to learn. And we're also challenged, and we're also, our heart is like, you know, before we start to teach, like, okay, will I be okay? So we're all the same. We're all humans. We all have the same fears. And also the professors that you may want to go to their lab, they're also like humans, and they also have to run to the next grant to get funding and stuff like that to maintain the lab, because like in the academics, our lab is like our own startup. Like we are the ones that have to bring the money and the funding to do the research. So don't give up. If you want to, don't give up. Ask how do you prepare the figures? Okay. Okay, so I can say that if I take figures from other publications, I just copy the link in order to give credit. Some things I have my students to help. So some things I told my student, do this and that, I want this thing, and they also help me a lot because I also give them a lot of tasks. And one of them is also to help me make good figures. That's to be honest. And the other thing is that I like aesthetics. Like I like things to look kind of like nice, and so I spend time on making things look nicely. So, but if you take something from someone else, always give credit. Like always. Okay.
Okay. So I think now I'll convey my vote of thanks. First of all, to everyone, the participants, first as a guest, as a foreign expert who has kindly agreed upon. It was way back in 2019 when people started proposing.
Am I the foreign one?
Yeah, you are the foreign one.
Okay. half foreign.
Yeah, okay, half foreign. Okay. So
Okay.
we proposed this course in 2019, and then it was supposed to be in the physical mode in 2020, but it's all because of the worldwide pandemic. So in that case, we had the interactive session through virtual mode, and then I thank Professor Hadas for accepting our request from my side as well as from Dr. Ram. And then thanks for agreeing, and then thanks for devoting your time for these 5 days with all along with us, especially with myself, Dr. Ram, and as well as with the participants. So with this, I take this opportunity on behalf of NIT Andhra Pradesh, KCT, and then GIAN, the local coordinator from the side of the local coordinator, as well as to the national coordinator. I thank you once again for delivering, sparing time with us in spite of your busy schedules, and enriching us with topics which are of so much needy, where it can have a wide footprint onto the consumer, otherwise it can be taken to the application side. So all these things doesn't stop only with the basic research, but it can be still applied onto the field. So with this, again, I thank one and all who are present here, especially the participants. Without them, this program is nothing. But again, thank you one and all. And I thank Dr. Ram as well for being there with me and then coordinating with all the steps for this program. Thank you, Dr. Ram, as well as Professor Hadas. And thank you, participants.
Very much. And also for the GIAN program for making this happen.
Yeah, thank you.
Thank you.
And Barani and Ram.
Thank you, President Dr. Barani, and to the entire participants. Thank you all, and hope we'll see you once again to some other course very soon.
Yeah.
Over to Dr. Barani.
Yeah, thank you.
Thank you.
So with this, we come to the end of the GIAN program. So I think we will close it up now. And then thank you all for listening to Professor Hadas, for myself and Dr. Ram. Thank you, participants. I think I'll be there in touch with you for another forthcoming days in order to get the feedback and then the certificate distribution. Kindly, if any mail has been there in your inbox for the feedback of the course, kindly fill those. Upon completion of the feedback, I will be circulating the certificate for this course. And the WhatsApp group for the participants will stay alive for another 1 week or maximum 10 days till the process gets complete. And then I will be sharing all the relevant information with respect to this course through the WhatsApp. So thank you, participants. And, thank you all.
Thank you and good luck to everyone.
Yeah, very good luck to everyone. Thank you.
Thank you. Bye-bye.
Yeah, bye-bye.